Hi, today we are looking at section 9.4, which is for Pythagorean identities. So this section, we go over 3 different trig identities for all based off of Pythagoras. So we're going to revisit the unit circle that we went over earlier in the course. So essentially, if we have a unit circle, so that means a radius of 1. Essentially, any point on the unit circle itself is given by cos theta sine theta. So that means that this side length is equal to cos of our angle, and this one is equal to sine of our angle. So if we did Pythagoras with this, that gives us sine squared theta plus cos squared theta equals 1. So that's our first identity. So this is one of our 3 main identities. Now our second one, we'll take that equation and divide everything by cos squared theta. So that gives us sine over cos is tan, so tan squared theta plus 1 equals 1 over cos squared is secant, so we've got secant squared theta. So this is another Pythagorean identity. And to get the third, we're once again going back to this original one of sine squared theta plus cos squared theta equals 1. And instead of dividing by cos squared, we're going to divide everything by sine squared theta. So sine squared over sine squared is 1, plus cos squared over cos squared is cotangent squared theta equals 1 over sine squared, so that's cosecant squared theta. So these are our 3 Pythagorean identities. Now, just because we have these 3 new identities doesn't mean we won't use the other identities, so we always have to keep in mind the previous identities we've learned. So from the previous section, we should also know our reciprocal and quotient identities. Now, just like when we did reciprocal and quotient identities, we'll utilize these identities to prove as well as solve questions. So, for example, prove each identity. We've got cotangent theta plus tan theta equals cosecant theta times secant theta. Okay, so just like in the last section, I will start with the side that seems more complex, so the side with more terms. So I'm going to start with the left side of our equation. So I'm going to span cotangent out to be 1 over tan theta plus tan theta equals cosecant theta times secant theta. Now, to be able to combine 2 terms, I need the same denominator, so I'll multiply this one by tan theta over tan theta. So that gives us 1 over tan theta equals tan squared, or sorry, not equals, plus tan squared theta over tan theta is equal to cosecant theta times secant theta. Now that these have the same denominator, we can add together what's in our numerator. So we've got 1 plus tan squared theta over tan theta is equal to cosecant theta times secant theta. Now, if we look at our Pythagorean identities, we had the identity that 1 plus tan squared theta is equal to secant squared theta. That means I can replace this 1 plus tan squared theta with secant squared theta. So that gives me secant squared theta over tan theta is equal to cosecant theta times secant theta. Now secant, we know is 1 over cos. So if we have secant squared, that's 1 over cos squared theta. And then I'm going to change tan in terms of sine and cos. Tan is sine theta over cos theta equals cosecant theta times secant theta. Now, if I'm dividing fraction by fraction, that means we can multiply it by the reciprocal of this. So we've got 1 over cos squared theta times cos theta over sine theta. So one of these coses will cancel out with one of these. Now, 1 over cos is secant theta. 1 over sine is cosecant theta. So we essentially have the same thing on each side of our equation, just different order. Now, when we multiply, order doesn't matter. So therefore, we have proven this identity. Next, we have cotangent cube theta equals cotangent theta cosecant squared theta minus cotangent theta. Okay, so obviously in this case, it seems like the right side of our equation is more complex, so I will start with it. So I've got cotangent cube theta equals, what we'll notice is both these terms have cotangent in it, so we can factor that out. So we've got cotangent theta times cosecant squared theta minus 1. Now, if we look at our Pythagorean identities, one of them has cosecant in it. So we have the identity that 1 plus cotangent squared theta is equal to cosecant squared theta. Now, this looks slightly different than this, but we can rearrange this. So if we subtract 1 from both sides, that gives us cotangent squared theta is equal to cosecant squared theta minus 1. So this now matches what we had in here, so we can replace it with cotangent squared theta. So we've got cotangent cube theta equals cotangent theta times cotangent squared theta. So that's cotangent cubed theta is equal to cotangent cubed theta. So we can say identity proven. Okay, next we're going to start dealing with some identities that involve fractions. When dealing with identities involving fractions, two things that can help are using terms with a common denominator. So we can combine what's in the numerator, or utilizing differences of squares. So for example, prove each identity. We've got 1 minus cos theta over sine equals sine theta over 1 plus cos theta. So on each side of this equation, we have a single term. However, if one on the right side of our equation has two terms in the denominators. So I would probably take this to be the more complex side and work on it. So I've got 1 minus cos theta over sine theta equals sine theta over 1 plus cos theta. So on a previous page, we mentioned utilizing differences of squares to help us solve it. So differences of squares with our denominators. So that means I'm going to multiply the numerator and denominator by the conjugate of this, which would be 1 minus cos theta. So I've got 1 minus cos theta over sine theta equals. Now, often when I do this, I won't bother multiplying out the numerator right away. If nothing cancels, then I will. But in the meantime, I will just leave this as is and FOIL out our denominator. So if we multiply out that denominator, that's going to give us 1 minus cos squared theta. Now, if we look at our Pythagorean identities, we've got sine squared theta plus cos squared theta is equal to 1. If I move this cos squared theta to the other side, that gives us sine squared theta equals 1 minus cos squared theta. So because we had 1 minus cos squared theta here, I can replace this denominator with sine squared theta. So I've got 1 minus cos theta over sine theta equals sine theta times 1 minus cos theta over sine squared theta. So this sign will cancel with one of these, so it leaves us with 1 minus cos theta over sine theta equals 1 minus cos theta over sine theta. So because both sides are identical, we have proven this identity. Okay, we have this one next. We've got 1 over 1 minus cos theta plus 1 over 1 plus cos theta equals 2 cosecant squared theta. So in this case, obviously, the left side of our equation is a more complex side, and we're essentially going to do what we did with that last example, where we multiply the numerator and denominator of each fraction by the conjugate of the denominator to create that difference of squares with our denominators. So I've got 1 over 1 minus cos theta. I'm going to be multiplying that by 1 plus cos theta over 1 plus cos theta. And I've got plus 1 over 1 plus cos theta. I'll multiply that by 1 minus cos theta over 1 minus cos theta. And that's equal to 2 cosecant squared theta. Okay, so expanding this out, 1 times anything is itself. So you've got 1 plus cos theta over, expanding our denominator, that gives us 1 minus cos squared theta plus 1 minus cos theta over 1 minus cos squared theta equals 2 cosecant squared theta. Now, we have the same denominators here, so we can combine what's in our numerators. So we've got 1 plus 1 is 2. Cos theta minus cos theta, those are just going to cancel out. So we've got 2 over 1 minus cos squared theta. And that's equal to 2 cosecant squared theta. So we've got this 1 minus cos squared here. That looks like it could be something from our basic Pythagorean identity that we can rearrange. So we've got cos squared theta plus sine squared theta equals 1. If I move cos squared theta to the other side, we get sine squared theta equals 1 minus cos squared theta. So 1 minus cos squared theta matches what we have here, so we can replace this with sine squared theta. So we've got 2 over sine squared theta equals 2 cosecant squared theta. Now, we could factor the 2 out. That gives us 2 times 1 over sine squared theta equals 2 cosecant squared theta. Now 1 over sine is cosecant, so therefore 1 over sine squared is cosecant squared. So we've got 2 cosecant squared theta equals 2 cosecant squared theta. So we have proven this identity. Okay, next we'll utilize this to help us solve an equation. So we've got 3 minus cos x minus 2 sine squared x equals 0 over the domain from 0 to 3 pi over 2. Okay, so we can see that we've got two different trig functions here, which is going to make it hard to solve algebraically. So what we'll want to do is convert them all to sine or all to cos. Now, we don't really have an equation right now that's going to change just a cos into something of sine, but we do have one that involves sine squared it and has cos in it. So we know that cos squared theta plus sine squared theta is equal to 1. If we rearrange to get sine on its own, that gives us sine squared theta equals 1 minus cos squared theta. So we're going to substitute 1 minus cos squared in for our sine squared. So we've got 3 minus 3 cos x minus 2 times 1 minus cos squared x equals 0. We'll expand this out. So we've got 3 minus 3 cos x minus 2 plus 2 cos squared x equals 0. We can combine this 2 with this. So we have, and we might as well reorder. So we've got 2 cos squared x minus 3 cos x plus 1 equals 0. I'm just going to, for example, say y is equal to cos x. And that gives me 2y squared minus 3y plus 1. We have a product of 2 times 1, so 2 with a sum of negative 3. We'll start each of these brackets of 2y. Two things that multiply to 2, add to negative 3 would be negative 2 and negative 1. We can divide the extra factor of 2 out of this, so that gives us y minus 1 times 2y minus 1. Then we'll substitute our cos x back in and rewrite it over here. So that gives us cos x minus 1 times 2 cos x minus 1 equals 0. Okay, so now if either of these factors equals 0, the whole thing equals 0. So we can write these as two separate equations. So we've got cos x equals 0. Or sorry, cos x minus 1 equals 0. And we have 2 cos x minus 1 equals 0. Now this first one, if we move the 1 to the other side, that gives us cos x equals 1. If we know our graph of cosine, we know that cosine starts at its maximum and then goes like this. We're going from 0 to 3 pi over 2. So between these two, we only have one place where it's at 1, and that would be when x is equal to 0. Now this other one, we'll move for 1 to the other side. So we've got 2 cos x equals 1. Divide both sides by 2. So that gives us cos x equals 1/2. Now we will draw this out. So we have our cast rule. Now cos is positive in these two quadrants. However, because we went from 0 to 3 pi over 2, that does not include this quadrant. So therefore, our answer must be in this quadrant here. Now cos is our adjacent over our hypotenuse. So you should recognize this as one of our special triangles. This side would be √3, which makes this pi over 3 radians. So that gives us x is equal to pi over 3. So we've got two answers. X is equal to 0 as well as pi over 3.